This is part 2 in a series of videos in which I'm developing a magnetic core memory system. The series of videos is really intended to promote a book I'm about to release that goes through this process in far more detail, but I thought I'd release these videos to hopefully raise interest in this subject. It is a fascinating subject, and especially if you're interested in vintage computing, then this is one of the cornerstones of early computer development. In the first video in this series, I went through the basic properties of the so-called square loop ferrite material, and it's called square loop because of the way it behaves, but we'll go into that in more detail in a future video. At the end of the previous video, I left off showing this curve on screen. This is obviously on my curve tracer, and we can see these two bumps that occur as a result of the core I have attached to the fixture flipping state as the current in the wire passing through it increases. So as the current increases in one direction, the magnetic field it's generating causes the flux within the core to reach a critical point, at which point it flips state, and the magnetization effectively is forced into one orientation, and then as the current goes the other way, we reach the same threshold but in the opposite polarity, and the core once again flips state. And in doing so, it creates a sudden change in the magnetic flux, and of course that generates a voltage or induces a current into the wire passing through it, and that's what's causing these two bumps. But how can we make use of this to store data? And so in this second video in the series, we'll look at how to change the state of the core magnetization as and when we want to, and then from that point on we can start developing a system to store data. So I'll move the camera across, we'll see what we've got set up on the bench, and then I can give a demonstration as to how we can go about starting this process. Okay, so what I've got set up here is a single core of the type we'll be using in our design. I've got 4 wires passing through it, but before I explain what this setup is for, just a quick comment on scale here. So this is one of the cores we'll be using in our design. It looks incredibly small, and it is. It's about 1.2 millimeters in diameter. Someone had to comment on the previous video about the larger cores I was using and would they be suitable for using a core memory. Those particular cores wouldn't. It's the wrong type of ferrite material, and the nature of the ferrite material used for the cores in magnetic memory is very different from the type of ferrite material used in filter cores and transformer cores. And it's a so-called square loop ferrite material that has very particular magnetic properties, and it's very different from standard ferrite material, so you wouldn't be able to use the cores I showed in the previous video for this purpose. I was just using those cores because they were big enough to handle and make a sensible demonstration from. But while we're talking about scale, as I say, this is a small core, but when we look at the size of the cores that ultimately were used back in the 50s and 60s, when this type of memory was at its peak, they were very much smaller than this. And in fact, this is a scale diagram showing the outer core is the same scale as the ones that we're using compared to the 3 that I'm showing inside, and these smaller ones are about as small as they got. They were down to between 0.3 and 0.4 millimeters in diameter, and as you can see, 3 of those will fairly easily fit inside the hole in the core that we'll be using. Even so, the cores we're using are incredibly small, but just bear in mind these were very highly refined and developed and did become extremely small. So what we've got is the single core, 4 wires, which we'll term as the X wire, the Y wire, inhibit and sense wires. I did say in the previous video that we'll be combining the inhibit and sense functions into a single wire. but for the sake of demonstration I'll start with 4 wires. It just makes it far easier to demonstrate what we're trying to achieve. And in this video what I want to do is just show the basics of how we can go about changing the state of the core magnetization, and how we can then read back the state of that core. And then in the future videos we'll go through how to put them together into arrays, and then how to develop some electronics to actually drive them. So the first thing we look at is what I've got hooked up on the bench here is I took the 2 wires that were going to the curve tracer, that's the yellow and the green wire, and I've now got them hooked up to the bench supply. Bench supply set to 2 volts but with a current limit of 600 milliamps. And if you recall, on the curve tracer these particular cores flipped state at a little over 300 milliamps. So 600 milliamps is easily enough to get them to change state. I have the supply coming through a push button, so it's a momentary button. I can push that to put a pulse of current through the wire passing through the core. It's connected to the X wire. I don't have the Y or the inhibit wires connected at the moment, but what you can see here is that the X wire will pass the full 600 milliamps and return that to the supply. So in other words, we can put a 600 milliamp pulse through the X wire by simply pushing the button. The direction of the current is dependent on which way around we have it connected to the supply, of course. That's normally taken care of by the electronics, which we'll look at in a future video, but for now we'll do all this manually just to make it as clear as possible. So we then have the first channel on the scope. So channel 1 on the scope is connected to the X wire, so we'll see a step in that when we push the button, and the point at which the step occurs in that trace is where we effectively start the process of handling the core. Channel 4 on the scope, that's the green trace, is connected to the sense wire. It's not connected to anything else, it's just going to read the output from the sense wire, and so we'll be able to see how the core responds as we apply these current pulses to it. So we'll start by arming the scope. I'll press the button to put a current pulse through it, and we can see that what we've got on the scope is the initial step where the current increases. And as I said, you can look at this in terms of the current. It's actually the voltage, but you can look at it as if though it's the current passing through the core. And then we can see we just have some ringing on the green trace, the output from the sense. There's no damping on this, there's no filtering. This is just purely what's coming out of the sense wire, and obviously we're getting some ringing on it. But there's no other signal. We can do this again, so if I press the button again, we can see we're getting a very consistent output. Does not look very useful, and it's not returning any information to us, and that's because the core is already flipped into the orientation for the current direction. If I now swap the 2 wires over that go to the supply so we can reverse the current going through the core, rearm the scope and press the button again. Okay, so we're getting a much more interesting output now. The scope is set up to 500 nanoseconds per division, and we can see that around 1 microsecond after the start of the current pulse we get this interesting hump appearing out of the sense wire, and this is occurring because the magnetization state of the ferrite core is flipping over, and the sudden change in flux is inducing a current into the sense wire, and that's what we're picking up here as a voltage. If I now rearm the scope and we send the current through in the same direction again, notice that we're no longer getting this lump appearing, and that's because we've already changed the state of the ferrite core so that it's correct for this direction of current. So nothing now will change, even though we are putting a current through the core that exceeds the critical threshold. because the core's already flipped, then it's not going to change state. So in other words, we now have information stored in the core. If we change the current direction yet again, rearm the scope and press the button, we can see that we're now getting a hump again, this time in the opposite polarity of course, because we're passing current through in the other direction. And this is caused of course because the core magnetization is flipping the other way. And again, if we rearm the scope and try to pass the current through again, it disappears because the core is already magnetized in the correct orientation for this current direction. So one more time, we'll just flip the wires back, rearm the scope, and we can see that once again we're getting the hump. Now unfortunately, as I mentioned in the previous video, the problem with magnetic core systems is that in order to read them you have to destroy the information in them. So the reason for that is we now know that this core is magnetized in this direction, and so we can pass current through it as often as we want and nothing will happen. So we can't read this core by passing current through in this direction. The only way we can determine which orientation the magnetization is in the core is to actually destroy that information. So if we assume that the direction we are currently applying is for writing information into the core, then the only way we can get the data out is to read the data by passing current through the other way. So we can assume that passing current through the other way is reading data. If the core is storing, for example, what we can term a 1, we'll get a lump, but we will also at the same time erase that data. So as we can see, we're getting a bump appearing, so we can assume that there was a 1 stored in the core. We've now erased that to a 0 of course. So if we read the core again, we're getting a 0. And that's how we store data. If we want a 1, we write a 1 by putting a pulse of current through to set the magnetization state in one particular direction. If we want to store a 0, then we just leave the core effectively unprogrammed. And then when we read all the cores back, the ones that show a hump had a 1, and the ones that don't show a hump had a 0. And of course we've also erased all the data, so this system we develop has to write the data back each time it reads it. Okay, so we now know how to change the magnetization state of an individual core, but we now have a problem to overcome when we put these into arrays. I mentioned previously that I will be making bare board sets available to anyone that wants to build this system, and this is the array board that I've designed for this system. It contains a total of 512 cores, so it gives us 64 bytes total storage capacity. And the way this is arranged is typical for a core memory system, in that we have a mat for each of the bits that we want to store. So it's an 8-bit byte we'll be storing, so there's a mat for each of those, and then there are 64 cores, one for each of the bytes that we're storing. But the way this is arranged is the X0 wire goes through all the X0 cores, so it goes through 64 cores, and the Y0 wire also goes through 64 cores, or the Y0 cores in each mat. And so the problem we have is if we select X0, Y0 for example, we're selecting the top left hand core in all the mats, and we might want to write a 0 to some of the cores and 1s to the other cores. But if we just leave things as they are, when we select X0, Y0, we would write a 1 to all of them, because they're all being selected with a current in both the X and the Y wire. So in order to prevent writing a 1 into the mats where we want to keep the value as a 0, we have the inhibit wire. and the inhibit wire goes through all the cores in each mat, so there's one inhibit wire per mat. It's also the sense wire, as I said, there's a single sense and inhibit wire, but we could just as easily have had a fourth wire going through every core on each mat. So what we do is we pass a current through the inhibit wire in the opposite direction to the Y selection wire, and that effectively reduces the magnetization or the magnetic field for that particular core. So if we were, for example, to energize the inhibit wire on this mat, so the net field would be only half that required to change the state of the core. So we do that for any of the mats that we want to keep the value as a 0, and it prevents the core from changing state. If we want to write a 1, we just don't energize the inhibit line, and then there is sufficient field to cause the core to change state. Okay, so I've now got the second channel on the supply set up for driving the inhibit line, and the blue wire connects the supply to the third wire passing through the core, which is our inhibit line. And one thing I'd point out here is normally we'd be driving the X and the Y wires to select this core, but because I'm only driving the X wire, I'm driving it with twice the current we would normally drive it with, but the overall effect is the same as if though I was using the X and the Y to select this particular core. So before we start, we have to decide on polarities, otherwise the system won't work correctly. So I'm going to assume that when I have the green wire connected to positive, and these two wires are the ones that are driving the X wire, so when green goes to positive, that's our write function, and when yellow is going to positive, it's our read function. And we only connect or pass current through the inhibit wire during the write operation. So we'll start off with the inhibit line disconnected, so no current flowing through the inhibit line, and we will perform a write. So that's with the green wire connected to positive. I'll arm the scope, but it doesn't really matter what we're getting out of the sense line here. We're not interested in reading the sense line during a write. We'll always get a hump showing the first time we do a write cycle, simply because we always erase the core whenever we try to read it. So we've now, in theory at least, written a 1 to the core, and so if we swap the two leads over and we do another read, we can see we're getting a hump. So that's indicating that there was a 1 stored in the core. As I've said previously, the action of reading a core will erase it, so if we try and read it again, we'll notice that nothing's coming out. So one of the functions we'll have to fulfill is to write data back into the core when we read it. So we'll change back to the write phase. So I've got the green connected back to positive. But this time I'm going to connect the inhibit line, so we now have half the critical current flowing through the inhibit wire, but in the opposite direction to the current that will flow through the X wire when we press the button. I'll arm the scope again, but as I said, we're not really concerned with what's coming out of the sense wire when we're doing the write, but we can see that we're getting a change of state in the core anyway, but as I say, we always would, because of the fact that we erase the core whenever we try to read it. We'll now disconnect the inhibit wire, swap back to the read mode, rearm the scope, and this time notice there is no hump. So even though we went through the write phase, the write cycle, because the inhibit line was passing a current, then we did not change the magnetization state of the core, and so when we came back and read it, there was no output from the sense line. So just to clarify this, we'll go back into the write mode, and do it one more time. So this time again I'll leave the inhibit line disconnected. Doesn't really matter what happens from the sense line at this point. Okay, so we've written a 1 to the core. We'll go back to read mode. And as we can see, we stored a 1 in the core. And we'll now write a 0 to the core. So this time, because we want a 0, we need the inhibit line connected. We'll do the right, disconnect the inhibit line, go back into read mode, and once again we can see we are reading back a 0. So in other words, we can now control whether we write a 1 or a 0 to the core. So even though the core is always being selected, we can use the inhibit line to determine whether we're going to end up with a 0 or a 1 stored in that particular core. And it's just up to us to make sure we control the inhibit lines based on the data we want to store in the core. Okay, so that's it for this video. In the next video we'll put together an actual driver circuit to try to start to automate this process. I won't be showing much of the schematics in these videos. They are detailed in the book, but I will be going through and explaining how they work, so hopefully the videos will be interesting and will explain the way these memory systems work. But I thought we've in this video covered how to change the state of a core, how to determine whether we'll store a 0 or a 1, and as I said, in the next video we'll look at starting to put together some electronics to drive all this.